Olá, meus amigos de Portugal. Apesar dessa aparência asiática, eu sou brasileiro. É uma pena não poder estar aí com vocês, mas vou tentar apresentar meu trabalho em inglês. Hello everyone. I just said that despite my Asian look, I am Brazilian and my native language is Portuguese, but I'll try to present my research in English. My name is Sergio Shimura, and today I'll be presenting our research entitled Precision Georeferenced Mapping and Routing with Drones for Pest Detection in Opuntia ficus-indica crops using RTK. This project was developed in collaboration with the researcher Arthur Miyazaki from University of São Paulo and Professor Michael Frye from University of the Incarnate Word, San Antonio, Texas. The Opuntia ficus-indica or prickly pear cactus is a crop of great socioeconomic importance, especially in arid and semi-arid regions of southern United States and north of Mexico. On the left you can see the actual farm where we ran our outdoor tests in Vinhedo, São Paulo, Brazil. The prickly pear crop's productivity is under constant threat from various pests. The most devastating of these is the Cactoblastis cactorum moth, as seen here on the larvae stage, but significant damage is also caused by cochineal, scale, and fungi. As you can see on the top right, the pad with black spots is the fungi, and the bottom picture with the white spots is the cochineal or scale. This pest not only cause direct economic losses for farmers, but also pose an ecological threat. The main challenge in combating these pests is detection. Traditional methods of manual inspection are labor-intensive, expensive, and most importantly, slow. By the time the damage becomes obvious to the naked eye, the infestation is often at an advanced stage, making control difficult and costly. As you can see on the right, there are several places of cactus moth damage, some very difficult to reach. This often leads to the indiscriminate use of pesticides with negative financial and environmental impacts. We need a faster, more precise, and proactive solution. Proposed solution: two-stage unmanned aerial vehicle UAV approach with AI detection. To address this problem, we propose an UAV ecosystem that operates in two main stages. On the left, the schematic drawing of the proposed method. We are using one drone for creating the high-resolution orthomosaic map and another drone to scan the crop. A wireless network used to send a video stream to the workstation that runs the AI model and creates the map with the disease location. As illustrated in this flow chart on the right, in the first step, a mapping UAV flies over the crop at a high altitude to create a digital twin of the plantation, a high-precision map. In the second step, this map is used to generate optimized routes for the inspection UAV, which in the third step flies low between the crop rows, sending a video stream to the ground station that performs real-time pest detection with artificial intelligence model. In the fourth and final step, a health assessment map is created. Now we go step by step. The foundation of the entire system is an accurate map. We conducted an outdoor test in Vinhedo, São Paulo, Brazil, using a DJI Mavic 3 UAV with RTK technology. On the image A, you can see the RTK antenna. In B, the whole property. The area of interest is highlighted with a white dashed line. Image C shows the location of the antenna, and the blue dots shows the locations of each picture taken during this flight. We flew at an altitude that allowed us to achieve a resolution of 1 cm per pixel. The centimeter level accuracy of the map was ensured by using real-time RTK corrections. The 57 images taken in the first step were processed using the open source software WebODM, generating the orthomosaic you see in the image B. This image also shows the first process of the image processing, the segmentation. Using a custom-made Python program, the rows were located and the lines were drawn, image C. From those lines, the center lines were determined and used as reference to the drone routes, image D. Step 4, AI Pest Detection. The final stage is the inspection and detection. The video stream from the low-altitude UAV is processed by the ground workstation with a custom-trained AI model based on the YOLO V8 architecture. You used an YOLO V8N model from Ultralytics retrained using a technique called transfer learning, where we added 4 new detection classes: healthy plants, scale, fungi, and moth diseases. This model has 3.2 million parameters and works with 640 by 640 pixel images. When a pest is detected, the system generates a geotag, a record containing the pest class, the detection confidence, and the precise geolocation. The outdoor tests. For the outdoor tests, we selected 10 pictures of different types of diseases and placed them in random locations in 2 rows. Then we tested the scan routes with the same DJI Mavic 3 drone and captured the video. From the 10 pictures, 7 were correctly detected and geolocation could be determined. The total route length was 144 meters, covered in 151 seconds, which gave us an average speed of 0.95 meters per second. And then this is the infestation map showing where the pests attacks were located. Conclusions: the proof of concept was well succeeded. Our expectations were focused in 2 primary challenges. First is the 55% accuracy of the AI model. For that reason, we expected false negatives. We got 3 out of 10. For a reliable real-world application, the AI model needs to be trained with a larger dataset, including more images with different light conditions. The second challenge was the inference speed, so we limit the scan speed. For the chosen speed of 0.95 meters per second, the model performed well, however the speed limit was not tested. For future work, as noted in the previous slide, first, we need a massive data collection for model training. Our model was trained with only 233 images. And second, we need to develop an integrated, user-friendly application. Thanks for your attention, and here's my contact information if you need further information. Thank you.